All right, so welcome back to part B, where I will attempt, hopefully more or less successfully, to do justice to the dark art of the Positivstellensatz, which sounds very forbidding and dangerous, but really it's just a way of talking about what is a good representation of a semi-algebraic set. And so that's really what we're going to focus on. I assume I won't do justice to it, but hopefully I'll be able to interpret it in a way which is consistent, at least, with the what we've talked about so far and understandable, and is also interpretable in terms of an optimization problem. Right. So to that end, most positive Stellensatzes are Stellensatzen, I guess that's German for plural, are interpretable using the geometric representation of our optimization of polynomials. So that's sort of their prima facie representation. So they consider specifically infeasibility of sets, right? So remember, in our optimization problem, which I talked about on the first slide of this lecture of part A, we reduced our polynomial optimization problem to its pure geometric representation, max t such that t less than or equal to f of x, or actually the set x comma t such that, and here I make this greater than or equal to, switch the sign there, g of x greater than or equal to 0 is infeasible. There's no feasible points. In ways, right? In a way, this is an easier problem to check than, right, the function on a positivity test, because what we're reducing it to is the question of, so if we have this representation of a set, so given a set of inequalities, and basically a set is a set of functions, right? F1, F2, which are true on that set for some point, right? So there's some point which these are true on the set. And what the Positivstellensatz is trying to do is take those truths, right, that they're true at a point, and use logical and deduction to try and determine whether the conclusion of those assumptions or those statements is that -1 is greater than or equal to 0. Right? So if you try and show that -1 is a valid inequality on that set, and if it is, it's obviously false, right? Because -1 can't be greater than or equal to 0. So it's a way of showing that a set is empty by showing that the logical conclusion of the existence of a set of point in that set is that -1 is greater than or equal to 0. Right? So with that in mind, let's consider the Positivstellensatz by Stengle. There are 3 Positivstellensatzes, well, actually 4, because we have weak version of Stengle's. And this says that the set is infeasible if and only if a logical conclusion of the sort of assumptions of the set is that -1 is positive. Basically, -1 is a valid inequality on the set. So not just a valid inequality, but it's a valid inequality which can be deduced through our set of 3 logical inferences, right? Multiplication, addition, and sums of squares, right? So remember, this is testable, right? And that's the important part. We can always test whether -1 is in the cone because we can search over that cone using sums of square optimization problems. Right, so okay, so what does that say? So -1 is in the cone. Basically, that means -1 is a combination of a sum of squares, which is positive, Squares, which are all positive. These are the variables. You should just highlight them. Variables, 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 variables. SOS, some positive things, and then positive things which are valid at least one point on the set. Right, so, and then in inferences, these are the monoids, and this is a SOS, right, those terms. So the inference then is that at a point, right, negative, we can just plug in that point here, and then -1 is something which is positive, which is obviously false. So we have an obviously false conclusion, therefore there must we have a contradiction, that if all of these things are true at least one point, we have that -1 is greater than or equal to 0, which is obviously false. Right? So the important point is that this is testable, right? So, but of course this is in the pure geometric representation, and so it doesn't actually look like what we're looking for. We want to test whether f of x is greater than or equal to 0 for all x in the set. So if we just make t 0, for example, right, and put a negative sign in front of f, right, then our two valid inequalities are f and g, right, in this case. So if we're looking then for positivity of a function on a set, if we want to show that f is positive on a set, then that is equivalent to infeasibility of the set of points x such that f is less than or equal to 0. And here I want to highlight the positivity point, because when we convert this to the pure geometric representation, we've lost that negative definite or positive definiteness, positive semi-definiteness, right? So this is not less than or greater than or equal to, it's greater than 0, right? So in order to get this term to be semi-definite, we need to make this term in the original functional representation greater than 0. So this isn't a problem in optimization where we made t strictly less than f of x. That wasn't a problem because, right, if you're optimizing over t, you can get one arbitrarily close, and so you've solved the optimization problem. But in our case, it's going to be a problem because, remember, we're looking for Lyapunov functions, and Lyapunov functions are sort of defined by v of x greater than or equal to 0. In particular, v of 0 equals 0. So Lyapunov functions are not strictly positive. So when we apply Positivstellensatz results, for the most part, 3 out of 4 consider strict positivity. And so we have to take these results slightly with a grain of salt, in that they don't really work for Lyapunov functions because v of 0 has to be 0. Now we could relax that or make it equal to epsilon, but that for Lyapunov functions, that's not something we can do computationally, so it's a bit of a problem. And we'll have that problem going forward. And it's just based on the fact that these Positivstellensatzes use this pure geometric representation where we've moved the objective to the constraint set. And when we move it there, we get less than or equal to. Whereas before we wanted f of x greater than or equal to t, right? Now when we move it to the constraint set, we have to, when we move it to infeasibility, we have to either switch this to definite or we have to switch this to definite. And semi-algebraic sets, at least in our definition, don't allow for definite terms in there. So we have to make this one definite instead in order to keep that one semi-definite. Right? So with that caveat, it still gives us a condition. So if we apply this to the question of whether a function is positive, right, strictly positive now, that's of course something we can't really relax. So if we move this to the constraint set, so then our first constraint becomes, so this is f1 now, and all these others are the other f's, right? So if we go here and we take our first f to be, right, take our first f to be the actual f, right, f naught if you will, in all of these terms, well, we can combine all of the terms that multiply it, which are these squares, and all the other terms in the monoid, and we can group them together and move them over to the left-hand side. Because remember, actually, we're trying to prove this infeasible for negative f, right? So when we're proving positivity, we're proving infeasibility of negative f less than or equal to 0, right? So that's where the positivity pops in. In any case, so now we've grouped all the terms which multiply f and pulled it over to the left-hand side, and now we're trying to we have an SOS optimization problem, and it's exactly the same as we had on the previous slide. It's just that we've grouped all the terms near with f. So here we've got our SOS variables. Here I've added q as a letter because I ran out of other letters, and so we have variables here now. So this is good. This is a necessary and sufficient condition, but it has actually a different problem in that sometimes, and specifically for Lyapunov functions, we want v to be the term we want to be positive. We want that to be a variable too. So if we make v or f a positive function, a variable itself, then we have this bilinearity in these variables. So in terms of proving infeasibility of a set, this is all very convex, and you can implement it with SOS. But in terms of searching for a function v, or a function f in this case, it's bilinear, and we can't really use it unless you just want to set all these terms to be 0, but then you're not using the p-sets. Nonetheless, this is the only Positivstellensatz which has no extra requirements on our representation, right? So it requires whatever representation you want to use, it's going to work. So no constraints on the representation. So that's an important point, right? So this is the sort of the most general Positivstellensatz you can possibly get, where you know nothing about the G, or you've chosen them very poorly so that you didn't think about them very much or whatever. But if you do that, then if you want necessary and sufficient conditions, we have a bilinear test, which of course can't be used because we can't solve bilinear problems, assuming that f is a variable. However, if we can choose our g's a little bit more carefully or a little bit more cleverly, we can actually improve this result. Before I do that, however, which is Schmudgen's Positivstellensatz, there is a weak version of Positivstellensatz, of Stengle's Positivstellensatz, which actually allows you to relax this inequality constraint to be semi-definite. This is actually the only Positivstellensatz that I'm aware of at the moment that allows you to do that, because they're all use that geometric representation. So basically, the weak version of the Positivstellensatz, weak actually it's stronger for us because we prefer this inequality constraint because we often deal with Lyapunov functions. If you're doing robust stability, however, positivity is just fine. But in any case, so it's exactly the same condition, except now there's one extra term, which is this one right here. Right? So it's basically, instead of having -1 there, which I think we had on the previous slide, or 1 actually, because we moved that over there, 1. From the previous slide, we replaced 1 with f to the 2q. So obviously, if f is positive semi-definite, right, all of these terms are positive semi-definite. This is positive semi-definite. And now if we have something, if we just divide, this is where the ratio of squares come from. If you divide by this term, so divide this whole thing by this, right? That's where you get the ratio. Then f obviously is equal to positive semi-definite, positive semi-definite, positive semi-definite, positive semi-definite, divided by something else which is positive semi-definite. And we're allowed to get away from the strict inequality because we don't have a 1 on the top. So if we had a 1 on the top, it would be positive definite, because 1 divided by a positive number is still positive definite. Well, in most cases, in any case. However, this doesn't really solve our problem in any way, because assuming we're trying to search for a Lyapunov function, because it's still bilinear, right, in our variables. But even worse, we have this 2q power here, right, for some power 2q. And if f is a variable, obviously when we square the variable, right, we get something which is quadratic. And so this is actually even worse from a computational standpoint, testing this kind of thing. So yes, we can do it, and we can formulate this Positivstellensatz, but we can't really use it very much. So neither version of Stengle's Positivstellensatz are we going to actually use much, unless you're solving optimization of polynomial problems per se, and in that case you don't care about the strictness of positivity very much. But in any case, this is the only Positivstellensatz that I'm aware of which deals with functions which are not strictly positive. So if we're trying to get away from, if we don't care about the positivity condition, if we get chill about the f of x strictly positive, then there are alternatives which allow us to resolve our bilinearity. Right? And the first one of those is Schmudgen's Positivstellensatz. So it basically says that f is positive definite if it's strictly greater than 1, right? So it adds a 1 here, right? And of course you could replace this with any positive constant and it would be equivalent, but that 1 in here is still an issue because it makes it f positive. So v's will, you have to drop the 1 term if you want to have positive semi-definite, and then you no longer have the Stellensatz. So, oh well. But in any case, so if you're looking for an f and you want to check whether it's positive on this set, well, you can search for a proof, right, or a valid inequality, or show that it's a valid inequality by combining these are equal to 0. This term is equal to 0. And here I've added back in the algebraic term. On the previous Stellensatzes, I dropped off the algebraic term just for simplicity because we're running out of space. But this one's a little bit more compact, so I put it back in. So t is arbitrary polynomial. It's a variable. Here, I should just highlight my variables. T, S, S, R, I, R, right? So that's greater than 0. This is greater than 0. This is greater than or equal to 0. Greater than or equal to 0. You still have to include all the terms in the monoid, however, right? So complexity is still high. So so you need a multiplier for each term in the monoid. And then there's the 1, which makes this strictly positive. If you want a sufficient condition, of course, you can just drop that off, but then it's only sufficient. Now, the advantage, of course, of this representation of Schmudgen's Positivstellensatz is that it resolves the bilinearity. Basically, we've dropped off the ratio, right? We've dropped off this ratio. So this is sort of the Positivstellensatz version of the SOS, right? So we've dropped off the ratio of sums of squares. And of course, if we do that because we want the linearity in f, right? If f is a decision variable, now this is linear in all of our decision variables. All the sum of squares ones, the polynomial one, and then what we're really searching for, f, which is often represents our Lyapunov function. So Schmudgen's Positivstellensatz, right, is less of a geometric one. It's a sort of semi-geometric representation version of the Positivstellensatz. But other than that, it's essentially the same as Stengle's, except for the multiplier here, right, or the ratio here, right. So it's essentially the same. And it says that it gives actually pretty tight conditions under which this is necessary and sufficient, basically positivity. So I guess in recent years, right, people have moved from these SOS problems to strict positivity, and that allows you to do a lot more. It is rather complex, has lots of SOS multipliers, right, because it have to include all of those products, right? So in like the linear representation, if we had 3 terms, right, if we had 3 G's, G1, G2, G3, Then how many multipliers do we need? Well, we need 3 here. We need products here, so that's 1, 2, 3. There's 3 terms here, and actually there's only 1 term there, so we need all of those. So there's actually 7 terms there. Right? And of course, we have another multiplier here. Fortunately for the algebraic conditions, we only need 1 multiplier, and it doesn't even have to be SOS. So that's algebraic constraints are a little bit easier in that sense. But still, lots of variables. And of course, if you haven't chosen your, there's relatively few constraints on the representation itself, except one, and it's a rather big one. Basically, it comes up in certain issues. Basically, it has to be bounded. The set that you're searching over has to be bounded in order to apply Schmudgen's Positivstellensatz. Which is okay if you're doing like local stability, so the ball is bounded, for example. Compact is what we call it, right? Closed and bounded. Since these are inequalities, we're always closed. So bounded is the issue here. This becomes more of an issue when you're trying to prove invariance of sets. So remember the butterfly set, where we were looking for a Lyapunov function outside of a manifold. So we were looking for a Lyapunov function outside of this set. And in that case, right, the set is not compact, which you're searching over. And so when you're doing invariant sets, right, we have an issue that you can't really apply Schmudgen's Positivstellensatz because the set you're searching for positivity over is not compact. So invariant manifold problem is tricky in this case. Nonetheless, it does resolve the bilinearity for most problems, so local stability in particular is the important one. The complexity is still high, however, and hence we're actually going to move on to another Positivstellensatz, which is actually probably, Schmudgen is not terribly useful because it's still complex and it requires compactness. So if you've got compactness anyway, then probably actually a better Positivstellensatz is going to be the next one, which is Putinar's Positivstellensatz. Putinar's Positivstellensatz, however, requires things about the representation which go beyond compactness. So I call it P-compact, P standing, I guess, for Putinar, since it doesn't apply to arbitrary Positivstellensatzes. And actually, the constraint on the set, so there's a set constraint on S x such that gi of x greater than or equal to 0, or am I actually using fi? I should use fi. Be consistent with my notes here. So it's a constraint on the set, but it's actually not a constraint on the set of points. So it's actually a constraint on the representation of the set itself. And remember, we talked about how the representation of the set and not the set is actually important for the results that we're getting at this point. So there's a constraint on the fi. So I say P-compact, but compact actually refers to a set constraint, and really what we're talking about here is a constraint on the functions. So that's, but it's dubious because, right, I mean, the constraint on the functions itself is hard to describe. So basically, the constraint is that there exists a polynomial with compact level sets. So that's hard, a little bit hard to quantify. So there exists a polynomial with compact level sets. So it, like, right, this is a problem because right, you can have a polynomial where like one of those level sets goes off to infinity, right? So that's not okay. So basically, it requires the existence of a valid inequality, or actually an element of the cone, of Fi. So that at H is the sum of squares plus these valid inequalities. So there's an element of the cone where we actually only require the first order terms here. So there's not every term in the monoid. Right. Such that all of its sublevel sets are compact. So again, right, it's on the representation, and it's tricky. So obviously, if one of the inequalities themselves has all compact level sets, then we're good. Then we're all done, right? However, right. So, for example, right, if one of the inequalities was the ball, right? So here's your set, for example, and one of the inequalities that define the set is Fi of x equals x squared minus b, for example, greater than or equal to 0, or actually b minus x squared. I get the other way around. Right. It's the ball, and all of its level sets are the ball, so that would be sufficient, right? So it's a bit of a problem because you can always add oh, I'm sorry, I'm off the screen. Sorry, down there. So if you have one of the valid if one of the representations, right, one of the elements of the representation was the unit ball, right, then you'd be done because all of the level sets of this are balls, and so they're all compact, right? However, again, it's challenging to verify whether a given set representation of your set is p-compact, and it actually reduces to an SOS test, right? So this is you can test whether you're in the cone, right? This is an SOS test. So if given a representation, right, you can test whether it's p-compact, but then that doesn't help you because what if it's not? So if you really, the goal is to be able to create representations which are pre-compact. And so really, like, these sufficient conditions I give down here are probably more helpful. So for example, if you can represent the region using only linear inequality constraints, not just one, but all of the inequalities have to be linear. So that would be like a polytope or something. So that's not actually very useful because this is rather rare. So this is not great. A better one, however, is that if you have a set and you're not sure whether it's p-compact, you can add a redundant constraint which satisfies the p-compactness criteria. So for example, if you're in Schmudgen's Positivstellensatz and your set is bounded, right, you can add a ball of sufficiently large radius to that representation, like add another constraint such that it contains the set, but it's just a ball, right? So if we just add the ball, then suddenly the set doesn't change, but it becomes p-compact because the representation is changed. You've added a term. So if you're not sure whether your term is p-compact, make sure it includes at least one unit ball. Or not a unit ball, add a ball, right? If not sure, make sure your set contains a ball of the form, right, b minus norm of x squared less than or greater than or equal to 0. And that will ensure that your p-compactness is satisfied. So, right, again, it's a property of the representation, not the set itself. So again, the representation is in this case more important than the set from a computational standpoint. So again, right, any compact set can be made p-compact by including a redundant constraint in the form of a unit ball for sufficiently large beta. So for example, consider a couple cases of the representations of the unit interval, right, a to b. Right? We considered that case, a, b, right? And actually, if we consider the representation x greater than a and x less than or equal to b, actually that by itself, if you have no other constraints on the set, that actually is p-compact because both are linear. However, if you were to, say, replace this one by x greater than a squared or something like that, that would not be p-compact because now this term is linear, but this one is not. Or if you were to add a redundant constraint, like x squared is greater than a squared, right? That would also not be necessarily, obviously, p-compact, right? Because it's now not all the terms are linear, right? So again, right, it's a term of representation. It's a little bit tricky. However, this other quadratic representation of the unit ball is p-compact, right? Because all of its level sets are p-compact, right? So this is the case where we have just that representation of the interval. And basically, this is a generalization of the ball constraint, right? So it's a ball centered at the midpoint, right? Essentially, that's what it is. So that one is p-compact, and this one is not. So again, p-compactness is a function of the representation and not the set itself. So if you can digest all of this, right, p-compactness, if you're willing to tolerate this p-compactness criterion on your representation, however, this is what we're going to define to be a good representation. And it's good in the sense that it dramatically reduces the complexity of the Positivstellensatz test, right? So basically, right, if your representation is p-compact, then we can drop off all of the products of the representation. Basically, almost all of the terms of the monoid except for the first order ones. So basically, it says that f is positive on this p-compact set if it's equal to a sum of squares. And here's just highlight our variables. Sum of squares, which are positive, multiplied by the representations themselves. And then, of course, we have the equality constraints here. We've added the algebraic terms back in here. These are 0, and multiply anything by 0, and it doesn't matter. So it's equal to something which is positive, semi-definite, squared, positive, positive, and 0, right? So it's clearly positive on the set. And what Putinar says is if your set is p-compact, then this is actually necessary as well, assuming strict positivity here, right? And here, the strict positivity is getting in our way again. But it clearly, like, since we don't have the 1 here now, we've dropped off the 1 from our term. We can use this as a sufficient condition, at least, or an relatively accurate sufficient condition, close to necessity, for positivity of Lyapunov functions, which is what we're going to continue with on the next set in part C. So this is actually the condition. If you remember back to part A in like slide 7 or something like that, this is the condition we proposed, and now we haven't advanced the computational test at all, right? Because we have the same set of variables. Now we can include f as a variable because it's linear. We have the same set of variables, but now we've given some guidance on how to choose our representation such that this test actually works. Right? So we've defined what are conditions on fi, or gi in this case, right? Such that this test works. And so now when we go back and try and test local stability and all these other things, we're going to be keeping this in mind and trying to ensure that our representations are p-compact. Our sets are the representations of our sets on which we're proving stability are p-compact. Of course, right, all of Rn doesn't satisfy this, right? And that's why, of course, it's because we don't have the ratios here, right? So positivity globally, right, requires the ratio of sums of squares. And we haven't done that here. If you think about it also, right, these GIs, right, what if you chose a representation of your set which had high degree, and you're searching for a function which is of low degree on that set, right? And that's really gets to the core of when this works and when this doesn't, is the degree matching issue, right? If you're looking for a function which is positive on this set, and like you just have, say, x transpose px, right? Well, then obviously you don't want your polynomials g to be relatively high degree, right? So, for example, in the S procedure, it worked when this was quadratic, right? And the reason now in the S procedure that we can restrict ourselves to a scalar tau is because this is quadratic, and now if we make this anything other than quadratic, right, the degrees won't match, and that's the problem. So again, in the linear case, or in the quadratic case for the S procedure, right, this would constrain our multiplier here to be a scalar. So now I'm going to pause again and then come back and apply this PSATs, these Positivstellensatz results, and actually we're only going to use Putinar's Positivstellensatz to the various problems that we posed for stability analysis, and particularly focus on local Lyapunov stability, and show how to implement the conditions that we proposed for representation of the cone with sum of squares tools. So pause it briefly and come back shortly.